Yeah, hi everyone, welcome to my talk about throwing tools at ranges. I'm very grateful that you're here today watching me talk. Ever since I talked about how to rangeify your code, I had a lot of people asking me, but how does it impact the runtime performance? Are ranges any good at runtime? And I did some benchmarks at my previous talk, but I didn't really analyze it in detail. And so I thought for this talk it might be helpful to use some kind of different tools and try to see how the ranges code actually performs. It's only runtime, it's not compile time. So first I'm going to start talking about my setup and how I generated the results. Next I'm going to explain the code that we're actually going to analyze. So if you want to compare your ranges talk to something, you need to have something else to compare it to. So I wrote the exact same code in what I call C-style C++, which does not use any standard library. C++17, which uses the algorithms, and C++23, where we use mainly ranges and range adapters. They all do the exact same thing, and I'm going to analyze these code examples with different tools, with Google Benchmark, Cachegrind, and the Visual Studio Profiler. And while I have used the Visual Studio Profiler before, I'm very new to the Linux tools, and especially as I mainly work on Windows machines, like in a private for my private use and also for work. But for you, the experience might be the other way around. And the presentation of the Visual Studio Profiler will be a live demo. Hope it will all work. And after that, we are going to optimize the code a little bit and then run the tools again. And then in the end, there's some conclusion. So let's start with the setup. As I said before, I'm a Windows user, always have been. And at work, we're also developing under Windows. So I really never had the inclination to learn Linux and its tools. So you might already be guessing that I use the WSL for the Linux stuff, which is the Windows subsystem for Linux. And so that's a virtual machine that installs Ubuntu by default, and you can use it like your regular Linux machine. And it's very easy to use, and it plugs into Visual Studio, and then you can use your Visual Studio on Windows and then connect to your WSL and build with GCC, for example. So it's super handy. The other thing that's interesting might be the computer that I'm using. If you saw this talk before, I had a very crappy laptop, and I managed to upgrade it, and I actually really like this one. It's not a gaming laptop or anything, but it's a good laptop. And and we will run the Visual Studio Profile on this laptop. But all the other results, the Cachegrind and the benchmarks from Google Benchmark, were created on this PC, which is my main PC. This is my gaming PC. It's a little bit more powerful, a tiny bit, just for the comparison. And if you think the speed doesn't match up with what I showed in the slides, that's because I used a different computer for both of them. And now we're going to the actual code. I tried to find a real-world example where I can use as many range adapters as possible. Turns out that's actually pretty hard. So I made up a nonsense code. So that's slideware. That's nonsense code. It just uses as many range adapters as I wanted to. It calculates something, but it has no meaning. It has no value. So you can get the code. It's on my GitHub, but why would you? Just, you can look at it in detail if you want to. Yeah, it's not going to help you with any real-world problem. Yeah, we start with the C++23 version. I wrote 3 sub-functions and then 1 function that calls them all. And this is somehow to mimic like a real-world problem or real-world code where you have like different functions that do something. And I'm very bad with names. It's called random. It's not calculating any random numbers. It's a random function that does random things, but it's not calculating random numbers. Sorry for that. And we start with a view that I really like, a view or range adapter that I really like, and it's called the Cartesian product. And the Cartesian product combines all elements of all ranges with each other, which is a fancy way of saying that this is a nested loop. And you put in all your ranges that you want to have in your nested loop. This range here is the outer range of the nested loop. This is the range, the vector that we input into the function. Then the second range for my nested loop is just an iota view that counts from 1 to 5. And then I do some transform also on the input view because I don't have like anything else yet. And now, at the end of the braces here, I have not done anything. I just made a huge view where all the elements are combined and they are stored in a tuple. It's called Cartesian product, and I think the name implies that something is multiplied there, but it isn't. It's just like the combination of all the elements. So now we have to do something with the range that we just created. And we use transform also for that. And as I said, we get all the elements in a tuple. And then I love to deconstruct my tuples. Usually I would give them proper names, but since this code is not doing anything like proper, I don't really have proper names. And then I do some random calculation, you know, as I said, just to do something. And as you might see, I am returning this view, this Cartesian view, or Cartesian view with the transform. The interesting thing about ranges or range adapters is that they are evaluated lazily. So at this point, even at this semicolon, and even if I return at this point, nothing has been calculated yet. What I'm returning from this function is a statement on how I want to have my elements calculated. This is the lazy evaluation. I only get the elements that I want once I trigger the actual calculation, and this is not this place. This is important for the ranges and range adapters to have in mind. For the C++17 version, I created a vector for the output, and I returned the vector from the function. So this is the first big difference to the C++23 code. This is eager. So if you compare lazy to eager, this is evaluated right away when the function runs, when the function is called. The C++23 one, you can call the function, you don't get any values, you don't get any calculations, unless you need the actual values of the range itself. So for C++17, I wrote also a nested loop because we don't have a transform variant that takes an arbitrary number of input ranges. We can have 2 input ranges, but we cannot have more of them. So I wrote out the nested loop. I'm using a range-based for loop, iterating over the outer range, iterating over my counting from 1 to 4, and then iterating over the inner range. And I do the calculation that I did in the transform view. I just do it right in the for loop body, and I push back the element. Also reserve the size beforehand. And that is the equivalent to what we saw before for the ranges, just with the difference that it's actually getting evaluated right away. And C-style is pretty similar. Don't be scared. There's a new. We will delete it later. And for C-style, I'm not using range-based loops. I'm using indexed loops, but it's the exact same thing that we saw before, just with more indices, more characters, and more stuff. And I'm also returning the dynamic array that I created. Then I have a second function, and for the second function, I really wanted to use CppTransform. because, as I said, with the standard algorithm, with the transform algorithm, you can only have 2 input ranges, 1 or 2 input ranges. But with a CIP transform, you can have as many input ranges as you want to, and you can put it into your CIP transform. It would be the same as having like a range-based for loop and then calling CIP and zipping all your ranges together. But this is also a very handy notation. And for CIP transform, you have to, so the first argument that you have to put into the function is your function that you wanted to execute. So in my case, it's a lambda that's just doing some random calculations. And this is built this way because CIP transform takes an arbitrary number of ranges. And that's a variadic template. And you know your parameter pack has to come last in your function. So that's why it's the other way around. So typically, if you know standard algorithms, the function that you want to execute, or the lambda, is the last parameter. But here it has to be the first one because of variadic templates. And then you input all your ranges that you want to do something with. And that's the CIP transform. I really like that one. Also, you see iota view here again. I start at 10, and I don't give it an end. And the CIP transform, also the CIP, terminates on the shortest range. So here, range 1, the first one that I put in is the shortest range, and iota will just terminate at the size of this range. So it's also quite handy if you have to do something like that. For the C++17 version, I again create a vector, and I'm not bothering with the range that I did with the iota range that starts at 10. I'm just having a variable outside of my std transform that handles these values, and I do the exact same calculation but on the std transform. And note, this is C++17, so we don't have range-based versions of these algorithms yet. That's why I use always range begin, range end. For C-style, it's pretty similar. There's a new again, don't be scared. I am. Then an index loop, and it's basically the same calculation as we saw before, but not in the transform, but in a for loop. Again, I'm not spending too much time on the code. You can look it up later if you're interested. And now for the third function, I actually have some temporary results. And so I wanted to calculate a partial sum. And in the previous version of this talk, I used range v3. That's what I forgot to mention. If you saw this before, I used range v3. Now I'm only using standard library. I'm upgraded to GCC 14, and now I can use the standard library, and there's no range v3 anymore. But range v3 has more range adapters, and it has a partial sum range adapter, and the standard library doesn't. Maybe it gets one in the next standard, but now we don't have any. So because I wanted to have this also as a view, and yeah, also as a lazy view, I wrote my own partial sum with this lambda. You might notice some cool stuff, like I initialize the sum with 0. I have this mutable keyword here. That means that the lambda that's a mutable lambda, and I can actually change the value of the sum in the lambda, because normally all of the values that you create for the lambda are const. And Andreas is sitting here. You can use his CppInsights tool to look. I think that's a perfect case to look at what a lambda is actually doing, and why maybe why your lambdas are not performing the way you want them to, and how they look to the compiler, and what does a mutable lambda actually change. So CppInsights is a great tool to look at things like that and see how this would actually, plan out. And also, typically in production code, I would not do this. I would write if I wanted to have it like this, I would write a function that is called partial sum, and I would do all the calculations in the function. Because the comments should describe why you're doing stuff and not what you're doing. So the what should be the name of the function, and then you don't need this comment anymore. So that's a rule of thumb that we have in our code base. If you see a comment like that, that is describing what the block of code beneath it is doing, this is its own function. It should be refactored out. This is its own function. Then I have a second temporary. I wanted to use a slide view where I iterate over neighboring elements. You can also use pairwise for that, or adjacent, also with the parameter 2. The difference is that slide has a runtime parameter for the window size, and adjacent has a compile time parameter for the window size. So, you can pick what you like. In the end, you get almost the same thing. Slide returns a subrange, and adjacent returns a tuple with the values. I could have used pairwise here as well because I have a known window size at compile time. And then I'm doing a transform again, just doing something with a substring, nothing important. And then in the end, I'm going to call inner product. And the numeric library breaks my heart a little bit because I think the standard library, the standard committee hates it. I love it because I think inner product is a very good function to have, and we don't even have a ranged-based version for inner product because it's in a numeric header and not in the algorithm header. I could write my own inner product, and I did before, but then I thought, well, I just use the variant that I have available, which is the one that which is the non-range-based one. It works fine, but it has a good name. You know what it's doing. You don't need to write it out. And yeah, I wish this would be at least range-based or range adapter. Range v3 has a range-based version of inner product. Yes, and also I need to offset the first input range here, because the second input range is one element shorter. Since you're doing something with the adjacent elements, your output is one element shorter than your input. That's just the result of dealing with two adjacent elements. Yeah.
In the case of inner product, because it only takes iterator and not a range, does it mean it's your responsibility as the caller to ensure the two input ranges are the same size?
Yes.
Okay.
But as far as I know, yes. Yeah.
Okay. But so in this case, because your input ranges are derived from the arguments of the parameters of the function, does that mean this function requires its input ranges to be the same size? Like RNG1 and RNG2?
Yes. Okay. They need to be the same size. Yeah. I'm also not doing any checks here, so I'm not checking for sizes. I'm not checking for empty ranges. I'm not doing any of that. Yeah. And one last thing I want to highlight in this for this code is that what we have seen with the ranges so far is lazy evaluation. As I said before, all of them are range adapters. Nothing has been calculated until we hit, I'm going to use my laser pointer, until we hit this semicolon. Because inner product is the first function that actually needs the values from my ranges. And that's where everything gets evaluated. That's important to know about lazy evaluation. Yeah, what I do in C++17, I basically the same. I have a temporary vector. I have a partial sum version in the standard library that I'm going to use here. As I said, I didn't want to use this in the C++23 version. I could have, but I wanted to have everything lazy until the inner product. And this is also eager, and I didn't want to have it evaluated at this point. Then I'm using adjacent difference, which is also a great example for a brilliant function with a terrible name. because you can calculate adjacent difference with this function, with its standard parameters, but you don't have to. You can get your adjacent elements, and you can do anything you want with them. So it might have just been called adjacent or something, adjacent elements, I don't know. But I give it a lambda, and I just do whatever I want with my elements. I don't care. So brilliant function, bad name. And then I use the exact same inner product call that I did before, but I need to offset the second temporary as well by 1, because that's a very annoying thing with adjacent difference, is that your output range has the same size as your input range because of standard library stuff. But the problem is that if you're doing something with adjacent elements, you know it's 1 element shorter, your output. And I don't like the design decision that they did, that they store the first element of the input range in your first element of the output range. If they had stored the last one, maybe, you could have just resized your output range to 1 size shorter, and then everything would be fine. But if you want to cut out the first element, you copy your entire vector in memory to cut out the first element that you don't need. And I think that's not, I don't know why it was done that way. I haven't done any research, but I don't like it. I think it's very annoying. And for the C style, now we have some new news. All of this is indexed loops. I didn't even bother putting a comment on that. I hope it's clear that I don't like this code. I don't think it's readable. I know it's very opinionated. I know people think this is way more readable than like the ranges version or the algorithms either. But I think if I look at this code, I don't know what's doing. So I would need a comment or like a good function name for that to actually know what it's doing or what's meant to do. So I'm not a fan of that, but it's doing the exact same thing. Going to have to believe me, and also here we need to delete the temporary so that we don't leak any memory, and we're just assuming everything goes okay until we delete the memory. And then in the end, I just call the functions. I have 1 vector as input, and this is the input for the first function. Then the output from the first function is input for the second function, and then those 2 outputs are the input for the third function. That's just how it is. You know, as I said, it doesn't make any sense. It's just how it is. Same for all the versions, including some deletes. So now the first tool that I use, that is Google Benchmark. And I really like Google Benchmark because it's platform independent. It's super easy to set up, and you can benchmark all your different versions of the code at once. To set this up, you write a static void function that gets a benchmark state as input. Then you do all your setup that you don't want to be benchmarked. Then you have a loop over the state. Then you do all the stuff you want to have benchmarked. As you see, I use the do not optimize version or option from Google Benchmark here because it turns out compilers are super smart, and they recognize if you're calculating something and you're not doing anything with the result, and then they might omit the entire calculation. So in order to prevent that, you can use do not optimize. And then you have this macro where you register your benchmark. I changed the output also to millisecond. Standard is nanoseconds, so it's always a huge number. And then you call benchmark main, and then you're done. This is the entire setup, and I think it's so easy, so easy to use. And then you get an output. So the first output is for the C style C++. We take 23 seconds with that code. C++17 takes 33 seconds, and oops. There is something maybe wrong with the C++23 code. We are going to figure out what it is. We're going to fix it. It's a spoiler. We're going to fix it. But yeah, so this is the first hint that something is off. So now we're going to Cachegrind. I always wanted to use Valgrind and its tools. That's a lie, I didn't. But I thought analyzing the cache usage of these different programs might be interesting. And so Cachegrind is a performance analyzing tool, and you can use it to optimize the cache usage of your program. And it tries to simulate the behavior of the processor's cache hierarchy and provide some insights into how your program uses the cache. So this is how you run Cachegrind for your program. There's a command line tool, of course, and you give it a bunch of different commands. The first one is it's part of the Valgrind tool set, but you want to execute Cachegrind. The second one is branch simulation, and it turns on the branch predictor. The next one is cache simulation, and here is between the first time I did this talk and this talk, there has been an update on Cachegrind, and I'm going to read from the release notes. Cache simulation is old and unlikely to match any real-world modern machine. This means only the RI event are gathered by default, but that's by far the most useful event. So they discourage you from setting this to yes. I still have the output with the entire output. I still think it's interesting to look at, but take it with a grain of salt. Even the Cachegrind programmers themselves say that's for modern machines, it's not accurate. And then the last parameter is your program that you want to execute. So I'm just going over all of the blocks. The first block that we're seeing is the one that you still get if you run Cachegrind with the default parameters, and then you get a bunch of other output that you now have to set up to get. So we're starting with the C-style version, and the first block contains the so-called instruction caches, or cache statistics. And an instruction cache contains the instruction to execute your program. When the processor needs an instruction, it checks the cache first, and if it finds an instruction there, then it can take it from there, and it's super fast. That's called a cache hit. And if it doesn't find your instruction there, it has to fetch it from main memory or another cache, and then it's slower, and that's a cache miss. So that's what you hear when you're talking about caches, like cache hit, cache miss, and stuff. And you want to optimize for cache hits, and you don't want to have a lot of cache misses. So we have different levels of caches. Level 1 is the fastest cache. It's the smallest, but also the fastest cache. And then your computer probably has more cores and different caches, and it can store more things in the lower level caches, which are a little bit slower, and the slowest is your hard drive. So if it's not in any cache, it is on your hard drive, and then you need to get loaded, and that's slow. Yeah, then we have data references, and this is very similar to the instruction caches. You have some data that you need to interact with in your program, like we have the vector with some values, and it needs to be stored somewhere. It's somewhere in main memory. It's not, might not be the hard drive, as I said before, it might be main memory. So yeah, I have some values that are in main memory. This is my huge vector. It doesn't fit in any caches. And now my program has to get the values from main memory, and depending on the index and where I am in my program. So I have some cache misses here as well. And you should strive to make the cache miss rate low. Also because accessing the data again, same with the instruction cache, is a slow operation. And the next block are the last level caches, and this is just bunched together like all your last level caches, higher level caches of the computer. And this last level cache, it consists of multiple caches, and it's the highest level, and it's shared among multiple processors and cores. So this is a larger cache, but it stores both. It stores instruction data and also it stores instructions and also your data. And then in the end we have branches, and branches in your code the branches that are used to execute your program. And this branches breaks down into conditional branches, and conditional branches change the program's execution flow based on a condition. And this can be in an if statement, it can be in a loop. Everywhere you have a condition, then you have a conditional branch change. And then you have indirect branches, and that is used to jump to a different address in your program, in your memory. And this can happen during function calls. And then we have some mispredicts. That's also when the branch misprediction happens. And this is when your processor's branch prediction mechanism predicts the wrong branch. And then if it predicts the wrong branch, then it's not in the fast cache, and then it has to get a different branch, and it has to load it, and then that is slow again. So again, all of the cache misses, all of the mispredicts you want to have low as possible. And with modern C++, you can try to optimize for branch mispredicts. I've never used the keywords, but there are keywords that's likely, unlikely to put into your code to maybe help the branch predictor to predict which of your branches is more likely to execute and which is not. But I haven't tried it yet. So we haven't really looked at the numbers yet. If I look at this with my limited experience, the program actually scores very well. We have a relatively high rate of data misses, but also the overall data misses are not that high, and we see it in comparison to the other programs. And then I have the same thing for C++17. Of course, you now all have the results that I just showed you in memory, and now you're comparing all the values. Okay, you don't have to. I did that for you. It's just if you get the slide deck and you want to see all the numbers, you can do that. So now we see the differences in the different versions. And you can see that the instruction refs are like super high with the C++23 code. And again, this is, has to do something with the performance issue that we have, and we're going to fix that. Also, I'm not quite sure why C++17 is also always that high. Maybe standard library has some more overload. Not quite sure, actually. What I found interesting is that the actual numbers of the instruction misses are super similar in all of them. All of them are 0%. And then also the data refs are way more in the C++23 version. But super interesting to see that the misses are extremely low for the C++23 version. And that has to do with the lazy evaluation. Because for all of the other programs, we create some temporaries, and we have more data in memory that we need to read and write to. But for the C++23 version, we don't have that. We only have one input vector, and we're calculating all the values that we need in place where we need them. That's why we don't have to go around in memory so much getting these values. Same, here the data miss rate is pretty high with the C style. I am no expert in that. I cannot explain why this happens. if you're experts in that, you can explain. Also, last level cache, there's not a lot to do with the C++23 version, again, because all of the data is in one input range, and it does not have to do all the reading and writing operations. And branches, also C++17, lots and lots of branches. I don't know why. I really don't know why. Maybe I should look into this with CPP Insights and compare. Maybe it works, I'm not sure. But again, super interesting mispredict rate, so that the actual numbers are the same across all of them. So So if I would want to optimize these programs, I would look at these three values. So, and now we are trying a live demo. So I'm going to use the Visual Studio Profiler. I guess you're familiar with that one? Yeah? Okay. Don't have too much time, so I have a main function for all of my three versions. I'm going through them. I'm in release mode, and if you want to execute your profiler, you go to debug, performance profiler, and then you have a lot of things that you can change. I never change anything. I just use CPU usage and hit start. I like simple tools. I like only clicking one button. And this took 3 seconds to complete. And now you have some statistics here. Not going over the statistics, not sure how valuable this is for C++ code. I think it's more valuable if you have like C# code and you want to see how much time you spend in calculations in kernel and how much time you spend in your framework or something. Typically, to just access this, I click any of these functions here. And then you have different views that you can choose. You have your caller, callee, call tree, modules, functions, and flame graph. And I like flames, so I'm going to the flame graph because it gives me a nice overview of where my program actually spends the time in. And it spends all of its time in main, which is good. We want to have that. And then I have my 3 different subfunctions. And as you can see, it spends most time in the third function. And so for the first round of optimizing the code, I would not look too much into the first 2, but I'm going to look into the one where I spent the most time in. And then Visual Studio highlights where we spend all of the computation time. We have 18% in this loop, we have 18% in that loop, and then we have 8% in this loop. And I guess it's this 8% here also belongs to this loop. It's not always super accurate, but you know typically where everything belongs to. And so my first thing that I would optimize in this is that I see I have 2 temporaries, I have 3 loops in there, and I can just smush everything into one loop. Therefore I can omit 2 temporaries where all the data reading and writing stuff in memory happens, and I can also speed up the execution time because I only have 1 for loop left instead of executing 3 for loops. So this is what we're going to do to optimize this version. And I think this diagnostic session was really helpful. Now we go to the C++17. Do the exact same thing, just hit start on the performance profiler. It's not a tutorial on the profiler. I know you can set up some stuff and things. Here runtime was actually shorter, but we saw in the Google benchmark that it ran longer. As I said, that's the difference also in the computer that I'm using. Again, I'm going to the flame graph and see where I spent all of my time in. Here I have a nice overview also of the different subfunctions that I'm calling. And I see the exact same pattern. I'm not surprised that I spent the most time in the third function. And that's because the third function, again, has 3 loops. It's a little bit more hidden because we're calling the algorithms, but an algorithm is a loop. And yeah, so the optimizing thing here would actually be the exact same as the C-style C++. Try to omit the temporaries, try to omit the loops. If you're optimizing for performance, you know, if your program is fast enough and you want to have it nice and readable and everything, you can leave it as is. But it just, you know, if you want to optimize something, this is a point that I would start with. And now we are going to find out why our ranges isn't performing so well. So let's see. I think that's the interesting part. Super fast calculation here, and now I have no idea. I know I'm in main, that's good. And then I am in this function, which is true. I'm not in this line, I'm in this line, but I spend all of my time in inner product, which is correct, because this is where I need my values to be evaluated. And then I have some memory address from the standard library, and I'm in inner product. This is correct. And then I am somewhere in the standard library, and I have no idea what's going on. I'm in advance. I'm advancing the elements and then getting the values. I don't know about you, but that doesn't help me figure out what's going wrong with my problem. Where are my performance issues? Why is this so slow? I tried to do the same thing in debug mode, and I prepared this beforehand because it runs for 3.5 minutes. So I thought maybe I see more in debug mode. It's not reliable in debug, and it will warn you about that, but sometimes you see something. So if we go in the output from the debug mode, we see a little bit more. But again, we are in our last function, we are in our main function, we are in inner product. This is inner product. But now I have a little bit more output. And as I saw this output, so something runs in parallel, and as I saw this output, this is actually the type of the view that we're returning and passing through our functions. And when I looked at the types, the one thing that kept coming back to me was the Cartesian product. It just came back to me all the time, and I saw it everywhere. And I thought to myself, well, wait, I'm calling this once. Why is Cartesian product everywhere? And so Cartesian product, as I said, is a nested loop, you know. And then I went back to the code and actually tried to figure out what's going on. Why is my Cartesian product everywhere? And the problem is me, typically. As I said, in this code, I am returning a description of how I want my values to be calculated. And this is the Cartesian product. And if we go to the function that calls everything, you see that we input the vector into the first function. And now you have to picture this. This range 1 is like your Cartesian product view and you know everything. And then I put this into the second function. And now this just adds to the instruction. So now range 2, this temporary, is Cartesian product of stuff and stuff, and then everything added on in the second function. And then I put all of these two descriptions of how I want my values to be calculated into the third function, and then it evaluates both of them individually. And that's the problem. And we will see in the slides how we can fix this super easily. But then not everything is lazy anymore. So, okay, we're starting with C-style C++. Again, I'm not going too much into detail. You know, I have to trust me that I merged all the 3 loops into one loop and everything works correctly. So the first loop went to this part here, it's a partial sum calculation. The second loop was the adjacent element thing, that went into this part of the loop. And then the third thing was calculating the inner product, and then that went into that part of the loop. So now this is the optimized version where just everything went into one loop to calculate everything. Now it's even less readable than it was before. You would need some comments, I think, on that. Yeah. And for C++17, as I said, basically it's the same optimization, getting rid of the temporaries, getting rid of the loops. But because I'm in C++17, I like to use an algorithm, and I used accumulate. Because inner product essentially accumulates a result of a product. Yeah, I like accumulate, so I used it here. And then optimizing the C++23 version. I showed you in the Visual Studio code where all my inputs are, how they trace through to the program. And again, range 1, range 2 contains instructions on how I want my values to be. But the range 2 contains the exact same instructions than the range 1. And then it gets calculated twice or evaluated twice. And then you have your big nested loop evaluated twice. To fix that, this is the code for that, I only changed one thing, and that's range 2. Range 2, we heard also at this conference, super, super handy. You can store your output of your views, of your adapters, of everything into a standard container or non-standard container if it fits the ranges 2 interface. You know, if I would return a pair, I could create a map. That's super easy. And since I use auto everywhere, I have to change nothing else. The entire code still runs, still works. This is the only thing that I had to change. But now this is not lazy anymore. This is evaluated eagerly. But in this case, I want to have that because I only want to have this big nested loop evaluated once. And this is how I force it to be evaluated at this time. So we benchmark this again. And we can see we cut the time in half for the C-style C++. We also cut the time in half for the C++17 version. And then for the ranges version, we're super, super fast. Just by evaluating the actual nested loop, we're super, super fast. I run this multiple times, and it's always slightly faster than the C-style version. And I'm really happy with the results. So I ran Cachegrind again. I'm not going into too much detail over this. You memorized the output from before, and you're comparing it now. I know that. Or I do this for you. So all of the stats went down on this as well, which makes sense. The program is simpler. It's easier. You have less temporaries. You have less loops to execute. Yeah, also the data refs are down, the misses are halved actually. The percentage is still high, but that's also because the data refs, I guess, are super low, and that's why the percentages are so high. Not sure if this is an actual problem, if you would have it in your code. Again, I'm not an expert. And the branches went down because the program is just simpler. You have less for loops, you have less things, your program is simpler, the branches went down. This is the C++17 version. Again, I compared for you. Yeah, so the instruction refs also went down, which makes sense. Same optimization as the C-style. The data refs also went down, which again makes sense. Less temporaries, less data to read and write from. And last level cache also went down, less work to do there. And also the branches went down, so the program is a little bit simpler than it was before. Again, makes sense. Still, branches are quite high with that. And then for C++23, if we look at that, we see instruction refs went way down. Also, data refs overall went down. but the misses went up. And now the misses went up because of the thing that I said before. Now we created an additional temporary instead of omitting one for the other parts. And now we have more data in memory that we need to read and write from. So we will naturally have more data misses. And also a little bit more things to do in the last level cache than we had before. Branches also went down. Yeah, and this is the comparison of all of them together. Not sure my animations work. Yeah, so I actually highlighted, at least before, where the which one is like the best one. It does not mean that the program is the best program. I mean, it's just stats, you know. I wanted to say this before. It's just stats. It does not mean just because your numbers are low on one part of the one version does not mean that this is the best program. You know, it does not have to mean that it's the fastest. So the C-style scores really well with the instruction refs and also the data refs and the branches, but it is slightly slower than the C++ 23 version with the ranges. So just because the numbers are high here doesn't mean that the program is bad. It just means, you know, this is something that you might want to look into if you're optimizing for a specific thing. So what would be next? Next, if the performance is good enough for you, I would stop there. But you can use the profiler again, see again if you can improve the code any further, where you're standing on that. Maybe you can use some other tools to analyze different things that you really want to highlight or improve. Yeah, so that would be the next steps. So to sum this up, I learned a lot about like Linux system, WSL, and so on by setting this thing up. And I really liked how it worked together, like the Windows and Linux, I really liked how it worked together. And there are things that you have to look out for in all of the coding styles that you're choosing to write your code in. And ranges are still very new, and their traps are not as well known as they are in the C/C++. So if you see a raw loop, you know, you have to check your index, you have to see that you're, you know, all the things that you're not running over your the memory of your container and stuff. So, but that's because we're used to it. We know what to look out for. But the ranges is super new, and this is what we need to learn how to look out for, or what to look out for. And the things that I ran into, the issues are not a ranges issue, but they were a lazy evaluation issue, because I'm not used to lazy evaluation, because everything so far that I did was evaluated eagerly. So this is a different way of thinking, and you have to keep this in mind when you're using ranges. And as you saw, the performance is really good for the ranges part without sacrificing readability. I know readability is also a thing that people debate on. Some people don't find it readable at all. I find it very readable. But again, as you get more used to using the feature, you find it more readable. And yeah, you should use different tools also to analyze different things of your program. I only used 3 tools here because I couldn't fit anymore. But there are more tools out there to analyze different parts of your code. And yeah, but one thing I want to stress is that I think we need a little bit better support for ranges and the lazy evaluation, because I don't know about you, but I couldn't figure out from the Visual Studio Profiler what is actually going wrong in my problem, where my performance, why my program is not performing. Because we're all in the standard library, we are in advanced. Yeah. It did not help me at all. So if you build tools, build a tool for that, help maybe visualize lazy evaluation, where it can go wrong. Yeah. So I think we need some more support for that. And yeah, that's it. Thank you.
So I have a question. The C++23 performance problem that you fixed involved eagerly evaluating a range that was used in 2 places.
Yeah.
So intuitively, I would expect lazily evaluating that to cause a slowdown of like 2x, but we actually saw it cause a slowdown of like 20x. Do you have an intuition for how that happened?
So my guess is that it's because of how complex the calculation actually is. It's not the laziness that's the problem, but it was a nested loop of 3 ranges. So nested loops are always, slow. It takes a while to evaluate them. And I think that's where the performance was. If the range would have been a simpler one, I may still be looking for where my program is getting slower. This was just super obvious because I saw this Cartesian product type like everywhere in the huge type name. But that was my only hint that this is the issue. Yeah, no more questions, and thank you.